All right, good afternoon, everyone. Welcome back. I hope you had a nice weekend. This is as I said near the beginning of the unit, this is a monster unit. It covers 3 chapters. Chapter 3 dealt with applications of differentiation in terms of rates of change. We looked at how position, velocity, and acceleration connect together with differentiation. And I'm not going to review that. That's all I'm going to say about it for now. We spent a full week dealing with different related rates problems. And then chapter 4, which we just finished, culminated or built up towards the concept of applying differentiation to determine solutions to optimization problems. We didn't dive right in. We looked at increasing and decreasing functions, different types of max and min, critical values, all of that. But it culminated in that application. Chapter 5 culminates in graphing. So we're going to be spending about 4 or 5 days learning about how different pieces of differentiation tell us different pieces of information about the graph of a function. And in the end, you will be able to graph, using the knowledge we gain, any function without a graphing calculator as long as it's not trigonometric or exponential or logarithmic or higher types of functions that you haven't learned about yet in terms of derivatives. So today what we're going to be doing is a quick review of some very fundamental ideas with sketches of functions, specifically x-intercepts and y-intercept. And we're also going to review how to find max and mins, which we call extrema. But then there's something new that we're going to learn which has to do with what we call symmetry. Functions can be considered odd, even, or neither. And this goes far beyond what we say about polynomial functions in Math 30. You know, when we say a polynomial function is odd in Math 30, that's not what we're referring to here. It goes deeper than that. It's kind of connected, but it's a bigger deal. So this is page 25 of your unit handout. We're going to review a few fundamental ideas here. It goes without saying that everybody should be able to determine a y-intercept of a function. And I pluralized y-intercept. I'm clearly talking about functions in general, like many functions. However, since we're graphing functions in this course, and a function is a relation in which every input has only one output, that means you cannot have multiple y-intercepts for a single function. Okay, the graph either crosses the y-axis in one location or it doesn't cross at all. But when you find a y-intercept of a function, you let x equal 0 and you solve for y. The reason for that is any point on the y-axis has an x-coordinate of 0. Pretty straightforward. If you're trying to find x-intercepts, and functions can have multiple x-intercepts because they go up and down, you let y equal 0 and solve for x. On the heels of that, I might as well repeat that and then tie it into the first statement. You can have multiple x-intercepts because functions go up and down. You cannot have multiple y-intercepts because functions do not go back and forth. If they did go back and forth, they fail the vertical line test, making them relations that are not functions. When finding local extrema, so I'm talking here about maxima and minima, you determine dy dx, you find the critical numbers, and you complete a first derivative chart. Everything we're talking about here and for the foreseeable future are open functions. We're not talking about closed functions, and we will review that when the time comes, but with a closed function, you don't need a first derivative chart. In fact, you shouldn't do one. So use the above 3 ideas to sketch the graph of this function. Okay, well, I think first of all, you should always look at a function in factored form to determine x-intercepts. Think very carefully about what I'm going to tell you. When we find a derivative, we want the derivative in factored form so we can just see what the critical values of x are, right? The derivative in factored form is useful because you can see the critical values of x. Well, the function in factored form is useful because then we can see the x-intercepts. So I can take out an x and be left with 3x to the 4 minus 25x squared plus 60. And I'll be honest with you, I started getting a headache at about 11 o'clock this morning, and it's just crashing down on me right now. So you have to be really on top of my math here, okay? So I'm factoring an x out, and I get 3x to the 4 minus 25x squared plus 60, and I think that's fine. Now, that, are we in agreement? Okay, that quartic factor, that 3x to the 4 polynomial, is also quadratic. We talk about this a lot in Math 20, that what makes something quadratic, essentially, is that the variable in the first term is squared, and the variable in the second term is to the 1, and the variable in the third term is to the 0. And I don't think we need to write it this way, but again, you know me, I'm here not just to teach you calculus, I'm here to teach you math and different ways to look at things. This 3x to the 4 is 3x squared squared. This minus 25x squared is minus 25 times x squared to the 1. And this 60 is 60x to the 0. And my point is, you have a variable of x squared in each of these terms. I'm going to amend this and write x squared to the 0. You have a variable of x squared in each of these terms. What makes this quadratic in a weird kind of way is that the exponent on the variable in the first term is even. It's 2. It's 2. Forget about even. The exponent on x squared is 2. Then it's 1, then it's 0. And you can recognize that as always being the case if the exponent just looking at it in every regular sense of the word, just looking at it regularly, you can recognize it as being quadratic if the exponent on x is even in the first term, half of what it was in the first and the second, and no x in the third. And I think what I see some of you doing right now is doing the b squared minus 4ac thing. Has anybody calculated that? Jay, do you have it? So, negative 95? Anybody else? Negative 95. Okay, so first of all, negative 95 is not a perfect square, clearly. Which means this is not factorable. And that, I don't know how much I want to review here. When you look at the discriminant, this goes back to Math 20. If the discriminant is greater than 0, then that means there are two solutions to the variable. So if we got a discriminant that was greater than 0 here, that would mean that x squared can equal two different things. If the discriminant is equal to 0, then the variable, and by variable I mean the blue highlighted thing, would only have one solution, which would mean x squared would only equal one thing. Now, by the way, because this is degree 4, if this were the case that the discriminant is greater than 0, there would be 4 solutions, because each of those x squareds equaling a number would give you 2 solutions. If the discriminant were equal to 0, then x squared would only be allowed to be equal to one thing, but that would mean x could be two things. Because when you take the square root, you go plus or minus. But if the discriminant is negative, so no, I want to stop. If the discriminant is a perfect square, those are special cases of this. That means it's factorable. The fact that b squared minus 4ac here is less than 0 I'm pretty sure you said negative 95, Jay. The fact that that's negative goes far beyond saying, oh, this isn't factorable. There are no values of x that make it 0. And I'll maybe be even more specific. This means there are no values of x squared that make the factor 0. But if there's no if there's no values of x squared that make it 0, then there's no values of x. What does that tell you? It tells you when you put this all together, and I've been maybe spent too much time on this, but I think it's valuable. I've reviewed here the nature of quadratics and the nature of solutions. And the solutions here, if you consider this to be equal to 0, are x-intercepts. So what that means is there is an x-intercept at x equals 0 because of that first factor of x. But because the second factor is a quadratic which has no solutions in any way, that's the only x-intercept. Okay? All right. How do we find the y-intercept? Well, the y-intercept is found by finding f of 0, and I think by inspection you can just see, looking at the original function or the factored form, when you put x equals 0 in, you get 0. These go together like peanut butter and jelly, okay? In my world. If I have peanut butter and I don't have any jelly, I don't have any peanut butter. I don't eat any peanut butter. They got to be together. If you have an x-intercept at x equals 0, it's going through the origin. Big deal. This is all we've learned in this whole discussion, is this graph goes through the origin. Okay. Now, what else are we asked to do? We're asked to use these three ideas. We've found the intercepts. There's only one for x and y. Now we have to find the derivative. So our function is y equals 3x to the 4 minus 25x squared plus 60x. Am I right?
You wrote down the one where you factored the x out.
Oh, thank you. Is this what it should be? Okay. So we have to find the derivative to find potential max-mins. So this is 15x to the 4 minus 75x squared plus 60. 3 times 5 is 75. Drop 1 from the exponent. 3 times 25 is 75. Drop 1 from the exponent. Derivative of 60x is 60. So again, we're going to factor things. dy dx is, we've got 15. By the way, I've designed this question so I didn't really care too much about the original function being factorable because that's just x-intercepts. I want lots of factors here. I want critical values of x. So that's why when we end up with x to the 4 minus x, 75 divided by 15 is 5, x squared plus 4, I believe that's factored correctly. The discriminant of this is a perfect square. This is factorable. And I don't know. I suspect that many of you just see that it factors into that. I mean, I know it's degree 4 and then degree 2, but the principle is the same. By the way, the discriminant, I believe, is 9, but not that it really matters because we know how it factors, but just to make sure, is it 9? 25 minus 4 times 4 is 16. 25 minus 16 is 9, pretty sure. So two numbers that multiply to give positive 4 and add to give negative 5 are negative 4 and negative 1. And this happens to give us two new binomial factors that are differences of squares. And that means that we're going to have the following 4 critical values of x in relation to the derivative. our critical values of x are -2, -1, 1, and 2, putting them in order from smallest to largest. So what does that mean? It means that at x equals -2, there could be a max or a min. Maybe there isn't. Similarly at -1 and at 1 and at 2. In order for us to find out which, if any, of these critical values of x are locations of max-min points, we need to do a first derivative chart. So this is, we got to go back over a week because we've been focusing on max-min and applied problems. Here we're just doing this. We're going from negative infinity to -2. We want to look in the subdomain from -2 to -1, from -1 to 1, from 1 to infinity, and to round things out from 1 to 2, and to round things out from 2 to infinity. Looks okay. Across the top, we can put all of our factors. We have 15, and then x plus 2, and x minus 2, and x plus 1, and x minus 1. The order in which you write the intervals on the left-hand side of your chart is important. The order in which you write the factors is not. We're doing this, of course, so that we can determine the nature of the first derivative, so that we can determine whether the function is going up or down, so we can determine where there's max-mins. I'm just going to lump the 15 with the x plus 2. This is what that first column looks like. X plus 2 is negative to the left of -2, and then when we pass -2, which is the 0 of x plus 2, it becomes positive. X minus 2 will remain negative until we pass the 0 of x minus 2, which is positive 2, then it becomes positive. I know it's been a while since we've completed these, but I think it's riding a bicycle kind of territory that once you learn how, you'll never forget. So I want to double check my work here. X plus 2 switches past -2. X minus 2 switches as we pass positive 2. X plus 1 flips when we cross -1. And x minus 1 flips across positive 1. It looks okay. So when we multiply across the top, the first row has 4 negatives. Negative times negative times negative times negative is positive. I use a different color to distinguish it, but you can circle it. 3 negatives is negative. These two pair off and give us positives, no matter how you look at it. And I go under the assumption here, you get that positive times negative times positive times negative is positive. Right? This is negative, and this is positive. So because our derivative is flipping back and forth across all of these critical numbers, by flipping back and forth, I mean positive, negative, etc., there are max-mins at all of these points. The function is increasing, then decreasing, then increasing, then decreasing, then increasing. So we have a max where these two intervals meet at -2. Then we have a min where the next two intervals meet, then a max, and then a min. And this goes back to the first derivative test, which we learned about, I think, right before we did max-min problems. That if the function is continuous through a number, we called it c, and immediately before the number, the derivative's positive, and then the derivative's negative, that must be a maximum because the function goes up and then down through that point. So what have we learned? There is a max at negative 2 comma something, a min at negative 1 comma something, a max at 1 comma something, and a min at 2 comma something. Did I remember the features of that table correctly? Okay. So now it's time for us to find the y coordinates. And this is simply a matter of putting those x coordinates in to the function. So you're going to put negative 2 in here. I want to say 38, but no. I want you to be very careful with what I'm doing here. There's a fail-safe way, or near fail-safe way, of me determining the y coordinates, and it's to use my calculator, but I do not want to cheat and look at the graph, okay? This is something you're going to have to force yourself not to do. And believe me, when it comes to the exam, there's a plethora of questions, a lot of questions that I can ask you in terms of understanding this stuff where you can't graph it. Okay, it's just not going to be possible. So 3x to the 5 minus 25x cubed, fourth cubed, 1 to the root of 5, 1, 2, 3, plus 60x. So just to make sure, I'm going to set my table at ask. I want to make sure this is right. 3x to the 5 minus 25x cubed plus 60x. And I'm just going to go in here and negative 16. I think this one might be 38, negative 38. And I want you to notice something interesting. Well, it will be of note in a minute. That when I put negative 1 in, I get negative 38 on this particular function. And when I put positive 1 in, I get positive 38. When I put negative 2 in, it gives me a y coordinate of negative 16. When I put in positive 2, it gives me a y coordinate of positive 16. So there's some kind of, the word is symmetry. There's some kind of symmetry here. So this is what we're dealing with. A max at negative 2, comma, negative 16. A min at negative 1, negative 38. A max at 1, comma, 38. A min at 2, comma, 16. You know, I suppose there's something else we can make an observation about, that this is what you would traditionally call in math 30-1 an odd polynomial function, meaning the highest degree is an odd number, which means the arms go in opposite directions. But clearly they go in opposite directions because the function starts by going up. So it must originate down in quadrant 3 at the negative infinity side of things. And it finishes going up, up, up. It does a whole bunch of stuff in between. So now we have to plot this. So you're going to draw a neat set of axes. And then you're going to scale things. So we're not given, oh, you're given a grid there. We're not given a grid with ticks on it. We make our own ticks. The important features of x is there's a critical number at negative 2, negative 1, 1, and 2. So we want to scale it to include those numbers. But we don't want to do this. Do I even have it? Might even have one here. No. We don't want to do this, right? I mean, something's got to happen before negative 2. So I would recommend that what you're doing is you're saying, well, let's call that 1 and this 2. And you're just eyeballing it. That's close enough. We're not, you know, designing nuclear weapons or landing people on Pluto. We're drawing, shucks, we're drawing a sketch, okay? Now what you want to do is scale things vertically to include those important numbers. Well, correct me if I'm wrong, but we had -2, comma, -16. Yes? And we had -2 or -1, -38. So the span of things vertically is that -38 is a pretty important number, and it's the largest negative number, the most negative number we are dealing with. But again, you don't want to do this. You don't want to say, well, this is -38. Let's just say -38 is, I don't know, here. So this is this point, -1, comma, -38. I don't even think we need to put a tick over here. I mean, if you wanted to, you could do this. You could say that's -40, and this is -20. But why confuse the issue?
This is from other photocopier.
Oh, thank you. Why confuse the issue or complicate things? Now, I want to point something out to you. Now, I didn't get out a ruler, but I can double check it. Did I scale things properly horizontally? Well, from this -1 to the y-axis is 2.2 centimeters on this ruler. That's close enough, okay? But I think what's important to understand is, and I can label this if you like, -1, -38, is that over here at +1, the y-coordinate's +38. And what that means is that and you can use whatever tools you have at your disposal, a pencil, a calculator, you can take a sheet of paper. What that means is that if I draw a line through the origin, that point over here at 1 must correspond to +38. There's that symmetry thing I'm talking about, right? I mean, if you said, oh, I'm going to put this point here, I'm over-exaggerating it, right? Clearly, that is not right. We go 1 to the left of the origin and we go 38 down. If you go 1 to the right, you have to go 38 up. You have to go the same distance up. In other words, and this is leading up to everybody, and you're not going to draw this line necessarily, it's leading up to the next little topic. That, don't muddy up your diagram, that these two have to be equal. Those two distances have to be equal. Because these are equal and these are equal, right? There's a symmetry here. It's an upside down symmetry or an inverted symmetry of some kind. But there you have it. So let me get back to where we are at here. And you know, my point, I guess, in light of everything I've said is you want to try to graph things accurately. You want a picture that later on, if you look at your graphing calculator, you go, yeah, that's pretty good. So we can label that point as well. And by the way, even down to the fact that I labeled -1, -38 below this point was by design, because it's a minimum. Right? It's going to be the bottom of a valley, so I'll have room to write it. Now we also have at -1, -16. Now -16 is not half of -38, but it's close, right? A little bit less than half. So it might be here. And again, if you were to draw or put down a ruler or a straight edge here, then when you get to 2, it has to be the same distance above the x-axis as that other point was below. I'm going to add something here which we've done before. You certainly don't need to do this, but I like it. And I didn't put it on yours, but if you were to draw a horizontal line along the top here, we can make a label that says dy dx, and there was something that happened at -2, something that happened at -1, something that happened at +1, something that happened at +2. The first derivative was positive, and then it changed to negative, then it changed to positive, then it changed to negative, then it changed back to positive. By the way, we can throw in our intercepts too, can't we? What does that tell us? I'm going to use the prime notation just to make it fit better. What does it tell us about the function? Don't forget, the function is what we're looking at. We don't see a graph of the derivative. Some calculus courses will get into what the graph of the derivative looks like. That's not what we're doing here. We're looking at what the graph of the function looks like. What it means is that the function is increasing and then decreasing and then increasing and then decreasing and then increasing. And that allows us to kind of get an image in our brain of what we're about to draw. The function is going to increase to this point, then it's going to decrease, and then it's going to increase. A little wobbly there, I'm not going to try to fix it. And then decrease and increase. This is what the function looks like. So whereas in Math 30-1 you would have no earthly idea where those other max mins are, where any of these max mins are, here we know where they are. I didn't label this, but if you wanted to, we could put in 2, 16, -2, -16. And, well, let's take a look at on our calculator, see how we did. First thing I'm going to do, well, I already entered it. I'm going to change my window settings to reflect kind of what I'm looking at here, which is, in the words of my grandpa, put near -3 to 3 horizontally, and I would say -50 to 50 vertically. Not too shabby. Looks pretty good. The last thing I want to mention, so I'll just pause there. Any questions with anything we did here to get this graph? Okay, the last thing I want to mention about this graph is looking ahead, and I think it's important to always look ahead, that the curve here has this kind of shape, and it has this kind of shape here. But it has the opposite kind of shape here and here. Something happens in this region here. There's an inflection point. And when you study inflection points in Math 30-1, you don't see them outside of the x-axis. It's always that inflection point on the x-axis. But there is, would you agree, I'll make the dot really big to kind of cheat the system, that the inflection point is within that dot somewhere. And there is an inflection point here. And there's an inflection point here. Well, that's related to the second derivative. And that's what we're going to learn in the coming days. Okay. All right, one more thing we want to look at today, which is new. This is something new. Functions can have symmetry, and there are two types of symmetry. If a function is symmetric with respect to itself, then it can either have an even symmetry or an odd symmetry, or functions can just not be symmetric in any way. A function is considered even if it's symmetrical with respect to the y-axis. So if you take a look at my hands, and the y-axis is the axis of symmetry of my body, if my hands were the shape of a function, this would be symmetrical in an even way. Basically, what I have on the left, if I reflect it across the y-axis, I get what I have on the right, on your right. And there's a test for that. Rather than just looking at things visually, because we don't always know what the graph looks like, the test is, what is f of negative x the same as? And if f of negative x gives you f of x, then it's even. What does that mean? Well, if I show you an example of a function, I hope you would agree that is even. It's a weird function. It's going to have a weird equation, but there is an equation that describes this function. And the reason it's even is it's obviously symmetrical with respect to the y-axis, but check this out. I'm going to pick a positive value of x called a, and I'm going to pick that point to determine a y-coordinate of the function. Would you agree that's the y-coordinate of the function, wherever it crosses the y-axis there, that blue line? Okay. Now if I go on the opposite side to the same value of x but the negative side of things, it's the same y-coordinate, right? I could take another one. So f of negative a equals f of a. I could take b. And this number where that horizontal line touches the y-axis would be f of b. What about negative b? It's the same number. And I hope you can see visually it doesn't matter where you go, to the left and the right, equidistant to the left and the right of the origin will be the same y-coordinate vertically. So what we conclude, since f of negative b and f of b are the same, is in general this is the case. A function is considered odd if it's symmetrical with respect to the origin, and I'll show you what this looks like in a second. By the way, the graph that we did was odd, had an odd symmetry. If f of negative x equals negative f of positive x, what does that mean? Would you agree this is symmetric in a twisted way through the origin? This is what we mean by odd. So if I pick a value of x called a, that is f of a. I go on the other side and look at negative a, that is f of negative a. So, whatever number this is, that number is f of a. Whatever number this is, that number is f of negative a. And I want you to notice that these two numbers are equal but opposite. So if this was 10, this is negative 10. What is f of negative a equal to? The negative of f of positive a. So that's what this statement is saying. It's saying when you put in a value of x and then a negative of that value, you get the same y, but they're opposite. Sometimes, well, in this case, when you put in that positive value of x, you got a negative number for y. And when you put in the negative, you got a positive. Good, I did choose right. It doesn't always have to be that way. When I put in this positive value of x, I get a positive value of y. When I put in that negative value of x, I get a negative value of y. All that is important is by putting in the positive and negative value of x, you get opposite values of y. So we conclude, since f of negative b is negative f of b and f of negative a is negative f of a, that f of negative x is negative f of positive x. A function is neither odd nor even if the simple fact is neither of those cases are true. So, I mean, we can look here at this function. I think it's clear that this has no symmetry. It's close, but not perfect. There's a value of a. What do I get? I get that number for y. Here's the negative value of a. You get a different value. We do not get the same value, and we do not get opposite. Since we don't get the same, it's not even. Since we don't get opposite, it's not odd. It's neither. Another example. No symmetry. Are you with me on that? So that's how we come up with these kind of definitions. But the fact of the matter is, without graphing, we need to know whether the function is odd or even. So how do we do that? Well, we need to find out what f of negative x is equal to. If we do this and we get f of x, we do this and we get the original function, then the function is symmetric and it's even. If we do this and get -1 times the original function, then the function is odd. So what does f of -x mean? Well, right, quick review of function notation. F of 3 would mean this, wouldn't it? F of diamonds would be 2 times diamonds cubed, no, to the 5 minus 3 times diamond. Yeah? So f of -x is what we get when we replace x with -x, and that seems weird, but you're accustomed to that. It's almost like a horizontal reflection, if you want to wrap your head around it. So we're going to get 2 times -x to the 5 minus 3 times -x. Let's see. I want to break this down for you. Again, my head is a little cloudy right now, but I don't think this is going too far, making it too simple for you. That 2x, 2 times -x to the 5, is 2 times -1x to the 5, which is 2 times -1 to the 5 times x to the 5. Right? And that -1 raised to the exponent of 5 creates a negative term. Negatives raised to an odd number become negative. So it's -x to the 5, and then this is plus 3x. And if I were to factor out, because I can, -1, I get that. But that is the original function. So what have we shown? We've shown f of -x is negative f of positive x, which means the function is odd. If you flip back a page and look at the function we graphed, it's odd. And one of the reasons you can tell this function or the one on the previous page is odd is that the exponents are odd. Now don't take that too far, because all the exponents can be odd and the function can be even somehow. We'll get to that. Does that make sense? This is why I knew when we graphed this previous function, the function on the previous page, it's why, even without looking at my calculator, I knew that these two numbers would be the same as these two numbers, but opposite. Because when I look at the function, take a look at it, odd exponent, odd exponent, odd exponent. Let's try one more. X cubed over 2x to the 5 minus 3x. So what we want to determine is f of -x. I'm just curious, how many of you see that this is going to be even? Oh, good. Will be -x raised to the 3 over 2 times -x in brackets raised to the 5 minus 3 times in brackets -x. Now, every exponent on every variable is odd, right? And that means when you put -x in everywhere, every term will become the negative of what it was. So the top of this expression is -1 x to the 3. I really hope you understand that although these two things I'm highlighting are equal, they have different meanings, right? In other words, this is not true. we're talking about in the part that's highlighted at the bottom of the screen is we have a coefficient of x cubed of -1. We've cubed the negative in the negative x. And then it's over -2x to the 5 plus 3x. So the question becomes, is this the same as the original function? Is it the negative of the original function, or is it neither? Well, I can factor a -1 out of the bottom. I'll go back to the -1x cubed on the top. When I factor a -1 out of the bottom, I get that. But those two -1s cancel. This, unless I've lost my mind, is f of x, isn't it? So after all is said and done, f of -x is equal to the same as f of x. So it doesn't matter when you use a positive value for x, you get the same result as using a negative, and that means that this function is even. I will kind of tell you this, that at least in terms of rational functions like this one, or polynomial functions like this, in order for there to be a symmetry, all of the exponents have to all be odd or even, or if it's rational, all odd on the top and or all odd or even on the bottom. I mean, if this were x to the 8 on the top, I hope you see with a bit of thought that the function would be odd, because the bottom would switch to the negative of what it was, but the top would still be positive. Positive over negative is negative. You'd be left with that extra factor of negative. So there's kind of shortcuts here, and that leads to this, that this is neither odd nor even. And it isn't, everybody, that the exponent on the top is even and there's an exponent on the bottom that's odd. The problem is the exponents on the bottom are not both odd or both even, and 0 is even. 0 is even. So if you were to put in -x, what do we get? We get -x. Notice I didn't say this, but I hope it was obvious. When you put -x in, you're putting it in brackets. Over 2 times -x cubed minus 3. We don't need to put -x to the 0. You certainly can if you like. But what I end up with is x squared over -2x cubed minus 3. The original function is x squared over 2x cubed minus 3. Thank you, Eli. The original function is x squared over 2x cubed minus 3. That is not the same as f of -x. These two things that I've written on both sides of the squiggly line are not the same. And the thing that's on the right is not -1 times this thing on the left. If it were, then the whole bottom would be negative. In other words, if the whole bottom were -2x cubed plus 3, then it would qualify as odd. Am I clear here? You're with me? Okay, that's it. So what we've done today is we've reviewed how to find intercepts, which is something you should know how to do anyway. We've reviewed the concept of forgetting about applications. That first derivative chart leads you to points you can plot, max-min points. And we've learned this concept of symmetry. So I believe on page 204, questions 1 and 2 deal with intercepts and max-mins. And on page 206, we're talking about symmetry. So get to work on that, please. I will come around and give you a hand. Probably tomorrow you'll get your next set of assignments. And now we're getting into a realm where quizzes are a real possibility. A symmetry quiz would be really easy for me to put together for tomorrow. As opposed to thinking last week, how am I going to give you a max-min quiz and not use the whole class? There's a little bit of a hint. Of course.